FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion, science, and engineering. I'm Ekaterina, and today we have a very first talk in 2022, and it will be a very special event, a masterclass given by Professor Tetsuo Tanabe, who will be speaking about retention and recycling of DT fuels in a fusion reactor. Professor Tanabe graduated and started his research at Osaka University in 1973. Then he moved to Nagoya University in 1995 and Kyushu University in 2005. He retired this university in 2016, and then he has been hired currently as a special appointment professor in Osaka University. His research interests are in energy conversion, nuclear energy, both fission and fusion, useful energy, securing safety, effective use of radioactive materials, artificial photosynthesis, and many others. A particular focus has been given to the research of plasma materials interactions in a fusion reactor, and he has published several books on this topic, including Tritium, Fuel of Fusion Reactors, Interaction of Hydrogen with Fusion Reactor Materials, and Plasma Material Interactions in a Controlled Fusion Reactor. So without further delay, I give the floor to Professor Tanabe.
Thank you, Ekaterina. It's a good, kind introduction. So I'll start this on this title. So it is my great pleasure to have opportunity to give you the talk. Anyway, this is a self-introduction for me. I have working on plasma material interaction and plasma phasing material for nearly 40 years. Since then, I have experienced now how research targets have been changing owing to the advancement and development of knowledge and researches on PMI and PFM. My research history is very parallel to the development of the research history in this field. So just show you some my review papers because this is very parallel. So first, I started graphite and plasma phasing materials. At that time, most of tokamaks employed carbon and resulting significant improvement in these days. And because of the high Z material has a lot of radiation, so they are hesitant to use that at that time. And then most of the tokamaks have changed to the carbon machine, but I am afraid that too concentrated carbon is dangerous, so I have claimed that studies on high Z as PM is necessary. And then I have done high Z limiter tests in Tetsuo because no one wants to use high Z materials in PF plasma phasing surfaces. So I tried to convince such kind of experiment in Tetsuo, and I have succeeded to do this. Since then, so because together with the colleagues of the URI Tetsuo peoples, I have made a lot of experiment on high Z materials on the plasma phasing. And then nearly around the 2000, tritium issues coming in because we are using tritium for a few fields. So tritium is coming in then still in this respect, carbon has high tritium retention. So people also, again, hesitate to use carbon. And ITER has decided to change the carbon wall to full metal machine now. Okay, but as again, I told you that for the fusion reactors, a high Z material might not be the best one. So we have to make a research on the other materials, other candidates. So the high Z is, in some sense, the comparison of high Z and carbon low Z materials is necessary. So I try to study hydrogen retention in tungsten, and I found that hydrogen detection in tungsten might not be small. So the carbon could be, in this respect, carbon could be the starting material. So that at the moment, my position is to use carbon as plasma phasing material in the reactor. In any way, we have to use tritium as fuel of fusion reactors. You know, the T is radioactive, of course, and T is also resources are not so enough. That is very poor. So T should be bred and fuel self-sufficiency must keep. This is quite important to make a fusion reactor as energy sources. And so the research for fuel recycling and retention, PEFS and phase surface and material and reactor become new challenge. And today's talk is concentrated at this point. Most of just talk are written in these three books already. Ekaterina introduced you. Tritium fuel of fusion reactors, plasma material interaction, control of fusion reactors, and interaction of hydrogen with fusion reactor materials. So that's a brief introductions. So today's talk is, this is divided 5 parts. First, give the introductions, and then second, fuel cycle in fusion reactors, and third part is fundamental of interaction of hydrogen plasma phasing materials, and the hydrogenization in tokamaks, particularly in the comparison with high Z and low Z materials, and then make a summary. Okay. In ITER and the fusion reactor, we face two new problems in handling of huge amount of tritium fuel for DT burning. But because of poor resources and activity or radioactivity T required simultaneous achievement of T economy and safety, which is not so easy. Detailed requirement to keep tritium economy in reactor are power generation compatible with tritium breeding, having enough margin in T breeding, a large T throughput due to poor burning. This is also important point. Optimized control due to fairing for efficient DT burning. Quantitative analysis of T and T plasma and the material. This is also very difficult at the moment. And I know isotope effect of differences in masses is very large, so the burning plasma. And large vessel inventory because of the poor burning. Investor inventory become large. These are the related to today's talks. So in addition to this, safety is another concern. But today I don't go into the detail of this type. So point is tritium confinement is a key issue for safety and should be realized with multi-confinement following the defense depth consent ICRP regulation. So the regulation law is established, so that we have to follow this regulation. So just I do say on this point. So the amount of hydrogen is very interesting to compare. You know, the hydrogen tritium. Tritium is often used for medical and tracer use and fluorescence. So signs of exist because there are no batteries needed. These are very small amounts of tritium is enough, and also, of course, weapons, fusion reactors, and also industrial uses. In medical or tracer use, they are using only picogram or nanogram. And chemical home is various. HTO is common, and safety control is easy because they are enclosed in the glove box or packages. And usually, T can be either in water or hydrocarbons. So this is very tiny amount, and the detection is very easy. But military use, in this case, tritium save might not be the first priority. Processes are rather simple. T is mostly handled with gaseous form and enclosed with the piping systems. And also, you know, they gave a lot of power, but most of the tritium are burned. So that gives require only small amount of 100 grams. Okay, industry use. This is quite totally different because they are using tons of hydrogens and they don't mind so some losses from the systems. And water, yeah, this is later I told you the water is quite important impurity in fusion systems, but industrial scale they don't mind. Some water is acceptable. Of course, hydrogen explosion is very important, so they should avoid it. To compare these fusion reactor, we are using kilogram water of tritium and deuterium simultaneously. So this system is completely different from industrial use of hydrogen and a strict tritium regulation law to keep safety and tritium accountancy. So D and T are handled simultaneously with variety of physical and chemical form in solid, liquid, gas, plasma, and energy. So variety of energy forms. And D and T always accompany non-negligible amount of hydrogen. This, please remind, this is very important point. In a reactor, poor efficiency in fueling, I will show detail later, poor efficiency in fueling and burning. Fueling in plasma and burning in plasma require large throughput. D and T behave a little different in fueling, confinement, escaping from war, and pumping because due to the large mass differences. HDT is mass differences 1, 2, 3. So this is very large. And controlling DT because they are mixed, so their control should be independently, but it is DT ratio can to make a DT ratio optimized. It is necessary to evaluate D and T and quantitatively failing of separately failing of DT. Failing deciding at plasma phase surface is also not well because this mixing is coming, so the response to the mixed plasma is not so easy to observe, okay, and also control. First, comparison of the property of HTT. Due to the large mass difference, of course, this is the inverse of density inverse. So the similar, so that 3 times, 2 times, and 1.5 times differences. So due to these large mass differences, physical properties, vapor pressures, melting points, so density and capacity, these are large different. But chemically, HD and T are rather similar. So this is characteristic of differences HDT. Okay. So tritium in nature is produced by cosmic rays, mostly high energy neutrons, and they neutron reacts with nitrogen, oxygen to produce some tritium. In fusion, tritium for fusion is mainly supplied from heavy water reactor in which the tritium is produced by reaction D and N. So the tritium is very expensive, and also the very small stocks, poor resource I show. And tritium decays okay, to the helium-3, emitting the beta electrons, half-life of 12 years roughly. The energy profile of the emitted electron is like this way. The average energy is 5.7, maximum 80.6 keV. This is very low. So the maximum range of beta electron is only 6 millimeter in air. Okay, in metals, this is micrometer. I'm sorry, on less than 1 micrometer. So shielding of this is not generally not necessary, but if it enters in your body, internal exposure is very dangerous. Okay. This is characteristic of this tritium beta electrons. So electron emitted neighboring molecule would enhance some chemical reactions. And effect of self-irradiation would be only very high concentration cases. And the decay heat due to these energies is around 324 milliwatt per gram, which could enhance T release. A little bit temperature could keep the temperature rise, but of course this is 100% of tritium. So that if tritium density is low, the heating is not so high. Oh, this is limit sources that show how the sources are distributed. You know, the natural abundance, which is given by the production by cosmic ray and decay of tritium, which is only nearly 5% per year. Okay, so this is balanced, and then remaining in the atmosphere is 2 times 10 to 19 becquerel. Okay. So there, after the second one, the large countries are making a lot of atomic bomb tests, and they produce a very large amount of tritium, which is 10 times higher than natural abundance. But this decays, okay, 12 years half-life, then the decays now remaining atmosphere is 2 times 10 to 19 becquerels. In ITER, okay, we will use tritium around 5 to 10 kilograms. So that this is very near to the natural abundance. So therefore, the tritium should be produced by DN reaction or using a leaching N reaction. Anyway, so the order, this is a order of the becquerel, and then 15 order of differences we have to regulate and account the tritium amount, which is very difficult to, because for the safety, we are concerned of this very small amount of tritium. So regulation should be done whole very wide range of tritiums, but this cannot be easy because method to determine such a wide range not possible. So we have to use a different technique, and then each have different, maybe different result sometimes. So no single method can cover whole range. Poor resolution in with cross-checking. So accountancy of the tritium is also not so easy. But in any way, we are in fusion reactor. We are concentrating tritium level around here. So they are escaping tritium. So this is for the importance of safety. Okay. So this is general instructions, and so this is a schematic of the fuel recycling and fusion reactor. Sorry, this figure is very busy, but in point is we are feeding the tritium and deuterium and to the plasma, and they are in the vessels, and some part are going to the plasma, and only tiny part is one to produce helium and neutrons and also energies. And then most of this throughput are recovered and refined and going back. Later, I'll come back to this figure more simple way. So because of poor fueling, only 20% are going to plasma, and burning 5% is in the plasma, only 5% burn. In total, only 1% of fuel pack is burned. Very high throughput. So the only 1% burn means 100 times of burn is we should put in throughput required. Okay. So compare the nuclear bomb. At that time, that is most of the tritium is burned. So they don't need a huge throughput or a huge amount of tritium. So this is quite different. They in respect of this large energy produced. So the fusion reactor needs large throughput, but of course most are recovered. Nevertheless, we need to large throughput. Plasma operation in the present tokamaks prefers. So that this is the next different subject. So in the plasma operation in the present tokamak prefers wall pumping of cells or low recycling, which is most of the input fields are going to the wall and stay there, not release. So this makes density control very easy because only input is the control. They, so they are from the wall, no return is coming back. So this makes density control easy. But in a steady state operation, plasma phase surface to be immediately saturated because the infusion reactor flux to the wall are very high. So most of immediately saturated, but most of the retention of the wall tritium is taken by the deposit because the plasma filtration source is eroded and deposited, and this deposition comes to the plasma shadowed area. They take a lot of fields, and this continuously increase with the time. So the to keep the wall retention very small is rather difficult. So in hydrogen recycling study in present tokamaks, only mass balance or simple recycling equation, the ratio of the input to output are considered. And released particles are assumed to be thermalized at the wall to the wall temperature, giving little influence on plasma. But in reality, reflected particles without fully losing their incident energy is not small enough to neglect, and hence power balance at PFM caused by hydrogen cycling should be concerned. This 2 points is today's main topics. So this is a simplified field cycling systems. So you put, for instance, 100 times 100 deuterium and tritium, and only 5% is going to the plasma, and among 20, only 5 again 10%. 20% is going plasma and only 5% is burned. So that means in overall only 1% of deuterium tritium is burned and then gives tritium. If the tritium breeding is 1.2, then it is gives 1.2 tritium. So, so assuming this wall retention, so 1 is going to the walls, they are removed. Then we recovered 98. Okay, 1, 2, 1, 1, 2 are removed, then coming back. So that means only we recovered 98. So if the breeding rate is 1.2, this does not satisfy the 100. That means tritium self-sufficiency is not attained. So we have to increase its burning coefficient, increase the burn under tritium, and also decrease its retention rate. This is required for fusion reactor to establish the energy sources. Okay, this is quite important point, but until now, we are not so much, very much concerned because mostly concentrated make a fusion plasma. But to establish a fusion reactor, this point is quite important. So I stress this point. Okay. So and also, unfortunately, the fueling efficiency is not so large, and also burning efficiency is also very small. So we have to increase both fueling and decrease the fuel retention rate in the wall to keep this fuel efficiency. Simple expansion can be made if the one, as I told before, the burn only 1, then loss. This is the loss. Okay, burn loss, and this decays rate 5%, but yeah, this is depending on how stored. But in any, and retention in wall or in the vessel, this I assume that 0.1%. Okay, So then total loss comes to something like 1.05. And the gain, so bleeding. So I assume that 1.3 coverage of the bracket of 0.82. That gives roughly 1.2. Okay, and then recovering rate, recovering rate. So if we assume that most of the tritium bullet are recovered, we can satisfy this. This is a little larger. So that this at the steady state, okay, to reduce T, it seems self-sufficiency would be satisfied, but tritium inventory, to reduce tritium inventory, it is necessary to increase burning efficiency as large as possible and decrease detection rate as small as possible. To keep self-efficiency, overburning ratio should be more than 1.6. All detection rates might be less than, in this case, to 4.6 or something. Initial inventory is also, this is a steady state inventory, but initial inventory later I'll show it becomes also important. Rough estimation, I can make rough estimations. How much T are burning in plasma? Assume the 10 kb plasma with density of 19, a plasma volume of 100 cubic, then total, including tritium in the plasma, is 10 to minus 2 gram, only 10 to minus gram per second. So T burning plasma 10 to minus, suppose burning efficiency 1% and confined time to 1 second, then it requires minimum throughput is 1 gram per second. Okay, so comparable with max throughput ITER, this is very comparable. So the maximum 200 Pascal per cubic meter is at 2.5 gram per second. Okay. How large will retention? Okay. T retain near, assume that T is only retained near surface. So one monolayer, for instance, absorptions means 10 to 80 times 100 square meters area. That means needs a 10 to 20 tritium. If surface layer is not 10 nanometer in depth saturated, then that comes 0.3 gram. And if 1 micrometer from the surface is saturated by tritium, by metal to atoms of the wall to H ratio 0.1, then this comes to 300 gram. So safety limit compared to safety limit of ITER vessels, 700 gram. This rather, so this is the main reason of this number is coming. Okay, and this exploration from the experimental evidence for carbon machine operated at 600 K86 operated at higher temperature. Exploited a few hundred ITER equivalent discharge that comes at 100 gram. Okay. This is very rough estimation of how large amount of dosage is required. So this kind of discussion suggests that at least steady state operation, utilization will fulfill the requirement of fuel self-sufficiency before coming to steady state, or in addition to steady state inventory, you need initial or immovable inventory, and dynamic detection is required. Among all T handling process systems, reactor vessels, bunker systems, and ICE systems have the large tritium inventories. And in the inventories, we can separate it 3 types: initial inventory, before attaining a quasi-steady state, and inventory at quasi-steady state, and also non-recoverable, gradually increasable inventory. So these 3 parts are separately discussed. Okay. In reality, we don't know how much initial inventory is. So I make a crude estimation at this point. Maximum, because any materials, particularly the metallic material, includes a high light hydrogen around something like 10 ppm. Or if tritium is exchanged by this hydrogen, then we are using something like 1,000 tons of construction materials. This and then this includes several kilograms to water, hydrogen. Then this in this exchange, so this means several kilograms tritium would be going to the fossil. Of course, this is too pessimistic explanation, but in any way, something like a kilogram order of tritium is required for the initial inventories. So, fuel sufficiency to attain the tritium fuel sufficiency require minimize T inventory, okay, and also recovering T inventory becomes important. The maximum efficiency of breeding and also recovery also, of course, necessary. So in ITER, in the case, low fuel rotation, because they are afraid of the tritium accumulation in the tokamaks, most important criteria for PM selection is low fuel rotation. That is the reason for selection of carbon, tungsten as plasma facing material. However, in reactors, easiness, we need a recovery, so to tritium, so they would be more important reactor criteria. So existence of residual H in the material is proved in the next view graph. In real discharge in tokamaks, so they are making a deuterium discharge, but this is not 100%. Because you need isotope changeover. This is the example of jet. During the hydrogen power discharge, they change to the fuels to deuterium. So they change over plasma in the plasma. So they need more than 20 shots, but still hydrogen remains 5%, and this continues very long. And this is case is from the hydrogen deuterium discharge to the hydrogen discharge. Again, this 5% of deuterium remains long. Okay. So this 5%, ITER is okay because ITER requires 5%. But for the burning point of view, this is okay. But from the tritium fairing and self-sufficiency point of view, it is too large. So it should be programmed, and also the existence of low hydrogen, normal hydrogen also gives disturbance of this. Next is fundamental of hydrogen cycling at the first wall. In recycling studies, people are concentrated on the flux balance, okay, how much hydrogen comes and how much hydrogen go up. However, in tokamaks, they carry the instant energy, okay, with the velocity. Also, radiation comes from the plasma, and then reflected or released particle carries the energy, and radiation also gives it. But in total, the very huge power is given plasma wall. So this disturbs recycling processes. And also, if you think about the mixtures, this flux balance are not, you can imagine flux balance is not so simple because retention time, retention coefficient in the material would not be the same between D and T. So there's such kind of particle, even particle balance are not so easy to determine or measure. So this point is more, we need a more detailed study of this. Okay. And in addition to this power, gives the change, alteration of the plasma facing surfaces. So power of radiation, also electrons, ions, and neutrons modify surface and bulk property relating BMI. So I don't want to detail of these damaging processes, but quite high incident hydrogen particles and also impurity ions gives defects in plasma hazing walls. Also in reactors, electrons also come together. So synergistic effect of electron and ions become large. Then they change recycling properties. The increase of hydrogen agitation through defect formation, and also decrease agitation through enhanced desorption by electron-stimulated desorption, and also surface roughening and shortcut path formation. So this makes very complex, and actually this kind of effect are seen in tungsten surfaces. Later I'll show you. Hydrogen is coming in and coming out. So this process, important point is hydrogen coming in at higher energy, and then they are losing energy and then thermalize and go back. So some are reflected back with high energies. Okay. So most important experiment is re-emission experiment, or injected this kind of high energy or low energetic ion, deuterium, in this case stainless steels, and then they are re-emitted from the surfaces. So high energy, they are going to very deep, they slow, and low energy, they can only shallow, then come back earlier. And also there is a differences with the incident energy. This is due to the reflection difference in the reflection question. Also deviation from the 100% is due to the deep penetration or trapping in the materials. So this showed everything occurring in the what happened in the plasma surfaces. In simple way, so the emission goes like this way, and this part are retained in the materials. And if you stop, then they decay like this way. But if you have a trapping in the materials, they are going to this way, and then continuously this kind increases. So the retention is similar, goes way. So the integration of this part comes to the total retentions going up. And if trapping occurs, there are no saturation, okay, gradually increasing. So if you beam stopped, you recover some. This is a dynamic or mobile retention. And this part are hard to recover. They are very slowly coming up. Okay, so from this we can study, but if there is a mixture of D and H and T, this makes a little bit more complex. So in present tokamaks, fuel retention rate is around, so that means input to output is 10 to 3%. This is too high. Okay, this should be below 1%. If the incident flux is high, then this saturation comes earlier, and this lower. So in ITER reactor, quite high incident flux, surface layer of PFM will be immediately saturated. Wall rotation does not change significantly with the fluxes, okay, nearly the same. But if you go to the high temperature, then their retention becomes very low. Saturation comes very early, and then temperature with increasing temperature, with increasing temperature, total retention becomes less. So because of high temperature operation, fuel retention rate could be significantly less than the present observed one, which is a few percent. So in high temperature operation, this is rather promising. Okay, so in re-emissions, they include reflected particles. I thought that this reflection is quite important because reflection question is not so small at low energy. This is a particle reflection, this is energy. Because the particle carries the energy, reflection of particle and energy is quite similar. One order magnitude different, not one order, because the scale is shifted one order to show this, okay? So nearly 10% of particle and energy coming back in low energy in case of hydrogen. But heavier the mass is, then this is decreased. So the tritium will be something like 15 to 20%. This is carbon. Okay. Reflection points are not so, which is not to be considered at the moment. If you go to the tungsten, reflection questions becomes very high. Okay. Heavier the regression question, higher. So the tritium, in case of tritium, most of the tritium should be because there are no data. This is a theoretical estimation. Okay. It is quite difficult to make an experiment with the reflection question, but nevertheless, reflection questions become very high. So quite large, and this could have significant because the wall loading becomes less, okay, with a high reflection question. But unfortunately, theoretical expansion below 50 eV is quite difficult, and the experiment is also very difficult. But please remind that reflection of particle at plasma phase wall is quite probably plays quite important role. This is clearly seen from the emission of the permanent emissions. In case of reflection, they are coming up with ions or excited atoms. Now, excited atom gives a permanent emission like this way. So the higher the reflection coefficient or lower energy, then intensity becomes higher. But higher energy, the reflection quite small, and also average water is large, so the intensity becomes low. This is so the reflection is very important, and also at higher temperatures, re-emission occurs not the molecules but atoms, okay, because hydrogen are dissociated like this. Okay, and higher temperatures, reaction go this way. So with increasing temperature, each atom becomes stable. So the emission at high temperature comes to deuterium. Okay, this is the same for the carbon. So this is because H2. This is H. So 2 times differences. So the molecules and atoms. Okay. So they are at very high temperatures, atoms are coming, and so the most of injected D is re-emitted. So the retention becomes quite small. This is very nice at very high temperature. And also the hydrogen, because of the hydrogen, they react with oxygen and carbon. You know this chemical element carbon. This is due to the formation of methane. But oxygen also, if there is oxygen on the surfaces, deuterium implanted in nickel, in this case, remove this oxygen to making D2O. Or in their existing oxygen in atmosphere surrounding, they also react with oxygen and produce D2O. So the chemical is very active. This response of the different tungsten and carbon clearly seen in this experiment. This is we say twin limiters, graphite here and tungsten here. And then we look for the line emission from this side. So this is the intensity of the DR emission from in front of the surfaces. Okay. In tungsten, because of the reflection large, and the emission becomes high, where carbon reflection is small. So and also this is this from this distance to the surface to the plasma. They decay. In case of tungsten, they are penetrated deep because the reflected velocity of the reflected part becomes larger for the high heavier materials compared to the carbon. So clearly there is differences in the hydrogen recycling in the mass differences and also the numbers. This deposition also clearly appears because this part tungsten reflection coefficient high, so deposition is quite small. While in carbon, deposition very large deposition appears, and also carbon. In case of carbon, deuterium includes very much. So that means carbon trapped deuterium like this way. So this is a clear indication of how different materials behave into the plasma. And next is high retention in so this is fundamental. Next is the high retention present tokamaks. So in carbon machines, carbon are eroded and redeposited very near. We say promptly redeposited. And repeating this prompt reposition and erosion, they are transported like from outboard side to the inboard side and deposited to the here or pumping duct. And so the net erosion, most of the plasma facing surface of net erosion, and this is deposition, net depositions. But first wall were eroded, outer diverter also eroded, and inner diverter deposited. Unfortunately, mass balance is still missing. So we assume that most of the eroded material is coming from first wall, but actually this is not measured. So this material transport is not completely solved. In any way, most of this deposition retains hydrogen, most are caused by cooperation of fuel with redeposited materials around here. This is shown here. In jet experiment, they are using tritium, and then they found a lot of tritium are deposited together with carbon on the plasma shadowed area, which is shown clearly in the tritium imaging. So this higher part, this part, okay, red part, retain the high amount of tritium here, and these are mostly in that plasma shadow, okay, deposited in plasma shadowed area. And deposition in the plasma facing surfaces, there is a difference in toroidal direction, poroidal directions. This difference is because there is a gap between the tiles. Okay, so to avoid the edge effect, there are some gradient, and then there is a differences, gap differences. So these part are eroded, and eroded part go deposited here, and then they include a lot of hydrogen. So this type, neighboring types are eroded and then deposited, and this is opposite to the higher field side. So this part is eroded and deposited. So in carbon cases, deposition retains a lot of hydrogen. Correspondingly, field retention rate in carbon machine is very large. Okay. In case of the torrent, this is operated at room temperature, so they're very high, 50% of the thing. but at high temperature operation, for instance, textile, yes, this is 8%. But if you go to more higher temperatures, all are saturated. So its retention rate is quite depend on the temperature of the operation. So high temperature operation or reactor is in this respect promising. So such high retention in fluorocarbon ore machine is one of the main reasons for excluding carbon at PMF ITER. In addition to large difference of reflection coefficient, so high reflection coefficient, carbon ore and tungsten ore are quite different in fuel retention. In carbon ore, retention is mostly caused by cooperation and deposit layers, while and this is immobile with making a CH bond. But in the tungsten, retention is caused by trapping near surface in addition to the solution. So deep penetration occurs in tungsten and diffuses a large dynamic retention, but these dynamic retention are recovered by diffuser release after injection stop. So this can be seen in clearly seen in the jet comparison of carbon ore jet ores experiment. Field retention rate in jet compared to the carbon cases and ITER-like very tungsten case, 2 orders of magnitude differences. So the field retention in carbon is actually higher. Okay, but interesting is, but failing. Okay, in case of ITER-like ore, they require large failing compared to carbon, which means that ITER-like ore takes, during the shock, takes a lot of hydrogen, but they are released afterward. So that comes down smaller in the retentions. Okay, so in case of the carbon cases, this is several times I told you the 3% something, but going to the tungsten case, this becomes 0.3%. So the large differences coming to the characteristic of the hydrogen retentions. In tungsten, a little bit complicated because the temperature dependence is not so simple. And also irradiation temperature, 500 degrees gives the highest retention. This is due to the trapping effect because various different kinds of defectors formed with depending on temperature, retention changed. So that if there are no trapping, the hydrogen retention should be going down with temperature like this way. So in case of tungsten, defect trapping is significant. And this significant, particularly in the paper deposited tungsten cases, they give very strong trapping side, and then hydrogen implanted VPS tungsten appeared over the 1000 Kelvin. Okay. Retention is large, and also at high temperature, tungsten traps the hydrogen. Okay, how, in case of tungsten, how hydrogen is trapped? Recently, tritium can be used to detect the depth direction of the concentrations. Okay, this is a linear scale, but if you go to the logarithm cases, because tritium can be made with a very wide dynamic range, so the profile is like this way. Okay. This is surface trapping, near surface trapping. This is just the solution. So this is clearly appeared in after 300 days. Okay, only this part, this is the dissolved hydrogen released, while trapped near surface remain. So this is clearly showed, and also most of the deuterium remain in tungsten is trapped one. So how this possible? So in case of the tungsten, the hydrogen going in, making bubbles. Also, the high power load changes structure of the tungsten to the grain growth. And then hydrogen accumulated here, and also hydrogen can be destroyed the grain boundaries, and then come to the smaller bubbles accumulated smaller surface briters, and this changes of the grain boundaries gives large exfoliation of grain boundaries. But this is quite consistent with the hydrogen profiles and appearance of the surfaces. Okay. So there is experimental data for the aspects that operated around and also high temperature detention measurement. Nuclear reaction analysis gives only the surface, and TDS gives a total retention. So, and also, please note that ITER limit is not 700 gram, but mean 2 times 26 to 20 for 500 meters. So square meter for 4 times 23. So that right around here. Okay. 10 to 20, some fluence of 10 to something. This. And also there is a differences on the bulk retention and surface retention. And this is quite consistent on this picture. So the surface, near the surface is very high trapping. So it's depending on the thickness, but nearly the similar amount of this 5 times 23 trapped in the surfaces, while diffusion, in this case, a little bit large penetrations. So this come nearly the same level of that. But this part are easily released after the removal implantation, and they stay only their surface trapped. This is the accumulation of tungsten, hydrogen in tungsten. While in case of the carbon is very special structure. So filters like a single crystal graphite, but defective, and they accumulated like this way. So even in plasma explosion, the structure does not change. Only the surface and bulbs are saturated like this way, and no diffusion in the filters. So, but hydrogen molecule, because they have open spaces, open pores, penetrated like this way, and then hydrogen concentration very high surface and saturated, and then only the near surface of this filters comes saturated and then decreases like this way. So the difference is given here, particularly large diffusion and no diffusion, but high saturation concentration. This is typical differences. So retention in carbon decreases with significantly decreases with temperature. This is the observed one. So the various part of the hydrogen concentration J260 is determined together with the temperature and plotted like this way. So that if going to 1,000 degrees C, very detention becomes very small. So accordingly, how fields are accumulated is measured. This is all right. So in eroded path flow, yes, this comes going like this way, and also deposited because initially deposited is small, but they are continuously increasing like this way. So deposition plasma shadowed area becomes high. Plasma haze so after long discharges, most of the tritium retention is coming from the deposition from the plasma shadowed area. Okay, and then there are some in the bulk, but because of the no diffusion, bulk detention does not so increase. Okay, this is only one measurement done in full tokamaks in 2060. Others are only point estimations. So I can compare the tungsten and graphite cases with incident fluences. Okay. So this is a square meter unit, but this is 100 square meters, so the two of them are difference. But in any way, carbon and tungsten is very similar. No, because tungsten, in case of tungsten, is operated at a high temperature. Okay, so this is 100% detection, and so this like ITER 1,000 shots. Okay. And so the fuel retention 0.1% is this line. Okay. So both tungsten and carbon can be satisfied the criteria of 0.1% retention. Okay. This is because the high temperature operation of carbon. So because of high temperature operation of reactor, fuel retention rate in plasma phase material 0.1% seems attainable both for tungsten and carbon, although 0.101 is difficult. Therefore, at steady state operation, the fuel sufficiency seems attained. But to attain the fuel sufficiency, we have to remove the tritium retained in the wall. Quite important. In addition, as I told you, the initial inventory, how much at the start tritium is accumulated is quite unknown and difficult to recover. This part is difficult to recover. So this 2 point is still remains, and also as a problem. And those deposit layer, so that because erosion of tungsten is very small, so eroded property of graphite and tungsten quite different. Okay, in case of graphite carbon wall, tritium is in deposit carbon in plasma shadowed area, but in case of tungsten, deposition is small, so the many part of the deposition is inside of the bulks of the tungsten and trapped one. So this is a little bit different. So in any way, in tungsten, in case of tungsten, still how deposition layer detain the tritium is not quite so certain, because in jet they are using beryllium. In case of beryllium, deposit takes a lot of hydrogen, like a carbon. So if pure tungsten, that might be different. So still it is unknown. Okay, so the time is running. So to use tritium, because of the poor resources and also safety and radioactivities, we have a new challenge, target or programs coming up out in PMI and PF studies. They are fair recycling and retention plasma facing surfaces, and also response of modified plasma surface, because high load power modify the plasma phase surface very much, and they respond to the plasma. So because of its poor resources and radioactivity, use of fear of fusion reactor requires special care to keep fuel self-sufficiency and T-safety. And to keep good confinement or easy density control plasma in present low fuel recycling is encouraged, while high recycling is mandatory in reactor because of very high fluxes coming to the plasma surface and remain desired target. Minimum fuel retention rate in present tokamak is around a few %, which is too large to attain feels self-sufficiency. It should be below 0.1%. But this seems possible if in a reactor, because of the first wall temperature would be around more than 500 Kelvin. So this respect, this is not so pessimistic, but initial input is still remains unsolved. For attainment of self-sufficiency, full recovery of remaining field in the wall, and also having enough margin tritium green necessary. So in these respects, the criteria for material selection of plasma facing material would be changed from low retention. Up to now, we prefer the low retention materials as PFM. But considering tritium self-sufficiency, more important is recovery. How we can recover the tritium in material. Poor efficiency of fueling and burning require large throughput or more than 100 times of one fuel. This makes the retention PA more the inventory in reactor vessels significantly large. Also, fuel recycling of PFM is not well controlled nor qualified. Flux and power balance and wall retention rate are not well known. So, re-emitted hydrogen is not necessarily sunlight to H, but release of H over even H plus having energy, which should influence further. So the low energy deflection from the first wall would be much larger than present tokamaks in reactor. So time is coming. It has been for us, of course, for you. It has been a dream to realize a fusion reactor as safe energy sources or green energy sources. Now seems attainable with ITER and beyond. Nevertheless, there still remain lots of challenges to overcome. I am convinced that you, young generation, could improve science and engineering to overcome the problems and establish the fusion reactor as a green energy source. So that's all what I want to talk to you today. Thank you very much for your attention.
Thank you very much for the very interesting detailed presentation. Now it's time for questions. Okay. And I know there is already one question from Mr. Martin de Jesus Nieto Perez.
Okay.
Please go ahead.
Go ahead.
Hi, thank you very much for the excellent talk, Tanabe. I have a question regarding the how will this tritium picture change when we consider the high neutron fluence environment on an actual machine? Will the neutron damage to both diverter and first wall materials change this picture of tritium drastically?
Yeah, sure. Neutron damage is very important, but neutron damage is most bulky. In whole volume is damaged. While high energy irradiation, high energy particle coming in is only concentrated near surface regions. From the plasma wall material interaction aspect, high energy ions and hydrogens keeps more influences on the plasma hydrogen recycling properties. On the other hand, neutron damage is bulk, and they make damage in bulk, so the hydrogen trapping, field trapping in bulk would be increased with the neutron damage. There is such a difference.
Yes, Professor Tanabe, thank you very much for your answer.
Yeah, okay.
I see one more raised hand from Alejandro Vasquez Cortez. Please.
Please, go ahead.
Yes, first of all, thank you very much for the interesting talk, Professor Tanabe. Then I have two small remarks. One of them is a bit more general. So you say that now you are under the opinion that it's better to have a material which tritium is easier to remove than focus on low retention materials.
Yeah, right.
Now, what type of procedure could we be able to use to remove that tritium during the operation of the machine? So, because it's not like you will have to stop the entire machine, disassemble everything, remove the tritium, and mount it again. So what kind of procedure could we use for that?
This is a good difficult question. Okay, there is a difference, tungsten and carbon. For me, the graphite is favored because hydrogen retention is concentrated in near surface regions. While tungsten, they are going to in deep, which means in some sense, graphite is easier to remove tritium.
Yes. Okay.
Yes. So this is the benefit of the carbon use.
Yeah.
So concerns of using tungsten is how to remove the tritium retained in tungsten. This is very difficult.
Yeah.
Okay.
Well, a problem for our generation, I suppose.
Yeah. This, I demand you this problem. You have to solve it.
I see. And then another small remark. So
yes,
you show some plots regarding the re-emitted deuterium from several heights set materials, such as I think it was molybdenum, tantalum, and tungsten, maybe.
Yeah.
What type of I think it was in slide 37, if I recall correctly.
Yeah.
What type of technique was it used to make such measurements?
So you know the line of sight mass spectrometer.
Okay.
If you use the line of sight of detector, your detector is the line of sight of the target, then you can detect the atomic hydrogen directly.
I see.
Yeah, so usually people are making residual deuterium gas. Right? In this point, you can measure deuterium molecules with quantum mass spectrometer as pressurized, right? But to detect the deuterium, because this comes to the wall, immediately recombine to D2. So you have to make a line of sight measure. So directly you have to detect the directly coming atoms by the mass spectrometer.
I see. Okay, thank you very much. I will take a look at the reference then, and I will read more in detail.
Sure.
Okay, thank you very much.
Welcome.
And we have one more question from Wang Min Zhou, please.
Yes, thank you, Professor. I have a question regarding to the tritium grading ratio. I think on the slides 9 or 10, you showed that the tritium grading ratio should be greater than 1.3, which is from my opinion, because I'm working on tritium grading blanket design for Udemo. This is nearly impossible for us to achieve.
Yeah, I know.
Is there a way? Is there a way to reduce this requirement?
So, difficulty is we are just breathing. So in the blanket itself, okay, but you have a coverage. So this means, of course, in overall blanket ratio 1.3 is not possible. You are right. Yeah. So it depends on how your blanket system. So you put it a lot of lithium, then you can get more tritium, but you lose at the same time you lose energy. It is a trade-off. You can increase. Putting more lithium, yeah.
Yeah, I'm not sure if I understood it correctly, because in the EU demo project, we have a TBR requirement of 1.15, which is already very tough for us
yes,
to achieve.
I know. Yeah, theoretically you can increase it. Theoretically you can increase. You put the more lithium-7, or then you get more tritium. But at this time you lose a lot of more energy, because to breed the tritium you need the energy. This is the endosonic processes.
Yeah, but at the other hand, we need to also to make sure the structure and the temperature of the structure
you're right. So,
within limits.
Yeah, you are right. Totally, you are right. Because from the engineering aspect, this is does not seem possible. Yes. So the people are thinking 1.2. Yeah.
Yeah, my question is there any possibility to reduce, I mean, from the fuel cycle side or from the plasma physics side to reduce this requirement?
So the decreases of these point. Or increases burning efficiency. Yeah, only the burn. So I'm not plasma physicist, but I strongly ask to increase the burning efficiency. This is very important in this respect. If you go this 2, that's okay. Yeah. Burning. Sorry, not one. Burning efficiency. I mean the burning efficiency should be higher. Otherwise, yeah, it is at present burning efficiency is so poor. Not realize high burning efficiency. So from the aspect of this engineering side of the blanket, yeah, you are doing quite well. So it is quite hard to get this kind of idea of burning efficiency. I agree.
Thank you, Professor.
Yeah, so that's a reason today I make a note. This 12 cycling tritium efficiency is quite important. Okay, I hope you understand.
Yeah, thank you.
Thank you.
Thank you very much for the interesting discussion. Any other questions? I don't see any raised hands now. This will be the official end of our webinar. However,